Alternating current is a current which varies in magnitude and direction with time and is represented by a sinusoidal graph. So in this case, the current or the voltage can be equal to I0 sine omega t. As far as omega is concerned, omega will be 2 pi over t, and t is a period for a complete AC wave. And in this example that we have, if the t-axis here is in seconds, then the t could be estimated to be about 6.25 seconds. And the next part to look at is the maximum or peak current or the maximum or peak voltage. So this is actually the peak current and the peak voltage, which in this case is actually 1 ampere. Finally, we could also represent the current in terms of F, the frequency. So in this case, I is equal to I0 sine 2 pi ft, 2 pi ft. And in this case, the F is actually equal to 1 over t, where t is the period of the AC wave. Next, we would like to introduce the phase difference. The phase difference could be calculated no difference from simple harmonic motions. You can take the time difference between here. So the phase difference between these two AC waves will be the change in time divided by t multiplied by 2 pi. That will give you the phase difference in radian. Let's take a look at the root mean square value of an AC voltage or AC current. Firstly, the root mean square value of an alternating current is defined as the equivalent value of the steady direct current which dissipates heat at the same average rate as the AC current in a given resistance. What that means is that if the root mean square value of an AC current is at 5 ampere, the amount of heat energy dissipated would be the same if we were to replace it with a direct current or a battery that has a 5 ampere current that passes through it. So how does one derive the root mean square value for a sinusoidal AC wave? This is the mathematical proof to allow one to arrive that the root mean square current is equal to the peak or maximum current divided by root 2. Similarly, the root mean square voltage is equal to the peak or the maximum voltage divided by root 2. Though these two are formulas that need to be committed to memory. Later, we will have an example to illustrate how we calculate root mean square value. It's important to understand the technique is that first you square the value, thereafter you mean it, then you rule it, as represented mathematically in this expression. With that, let's take a look at some examples. The first example we're looking at is the sinusoidal AC wave. Like earlier as proof, all we need to do is to apply. So this is the AC sinusoidal wave, and V0 is the maximum or peak voltage. So in this case, Vrms is equal to V0 over root 2, and the Pmax is V0 squared over R, assuming that R is the resistance of the load that the AC waveform is being applied to. Finally, when it comes to P average will now have to take the Vrms value. And you have to remember the root mean square voltage is similar or equivalent to the voltage of a direct current. So in this case, will be Vrms squared divided by R, and Vrms squared we can actually replace with V0 squared divided by 2. So from here, hence from here we know that the average power dissipated in the load resistor is half that of its maximum value. So let's take a look at what happened if you're able to fully rectify the AC current, and later we'll show you how we can do that using a diode. And when you fully rectify an AC current, you'll find that the AC current all flows in the same direction. So like depicted here, okay? And we now know that all these formulas will still be the same. The reason is because that when you work out the root mean square value, in actual fact, when you work out the root mean square value, you actually square every of the voltage value, and you'll get a graph very much dotted in the dotted form. And then you sum up the area under this graph. And after you sum up the area under the graph, you will then divide by actually the period. And you will then divide by the period. You will find that if you do likewise to calculate the root mean square voltage for this fully rectified wave, you will realize that the area under the voltage square graph is exactly the same as this, and hence the root mean square voltage is the same. And if the root mean square voltage is the same, the P average will also end up to be half that of your Pmax. However, let us now take a look at a half rectified wave. A half rectified wave means this part of the voltage that's applied across is actually being removed. So in this case, in the full cycle, you only have this part of the voltage. So therefore, the root mean square value of this part, which originally, if you have two of this waveform, ought to be V0 squared divided by 2. Because the area under this, there's actually two waveforms inside here. But in the case of a half rectified wave, you only have one. So I have to multiply by half. Therefore, because of that, the root mean square value for this half rectified wave become V0 divided by 2. And therefore, the P average become 1/4 P max. Let's take a look at another second example. In this case, you'll be looking at a non-sinusoidal alternating current. So the peak voltage is now V0. For us to work out the root mean square value of this AC waveform, we will first have to square the value first. So if you square all the value, this value V0 becomes V0 squared. Then thereafter, we have to sum up the area under the graph. So in this case, it will be V0 squared multiplied by T over 2. For this part of the graph, which is negative V0, after we square it, it's also V0 squared. Then I also multiply by T over 2. Then we have to take the mean. In order to take the mean, we have to divide by the entire T itself. And therefore, because of that, if you work out the math, you realize that end up the V root mean square is in actual fact the peak or the maximum voltage. Hence, the P max still remains the same, but the P average now is actually equal to the P max. Let's take a look at what happened if we manage to fully rectify the wave. If we manage to fully rectify the wave, the steps that we undertaken to calculate the VRMS and the P average will exactly be the same. Finally, let's take a look at what happened when it's a half rectified wave. If the wave is half rectified, this portion will now be removed. Therefore, because of that, in terms of the area, in terms of working out the root mean square voltage, we will now have to square the V0, which is V0 squared, but in this case multiplied by T over 2, and we will have to now divide by T. Because this part here, there's no voltage that's been applied across, so it's 0. Therefore, you work out that the mean square value will be V0 squared divided by 2. Therefore, the root mean square voltage will be V0 over root 2, and from there, your P average will end up to be half P max. Finally, we want to take a look at there's one twist in the exam question which they always ask. They will ask to say that what happened if now you decided to change the frequency or the period of the AC wave. Say, for example, we multiply by 2. So the period has now increased. Okay? When the period has increased and the frequency has dropped or has changed, end up whatever formula that you have here does not change. Let's show you the proof. So if, for example, like we explained, if this become 2t and this become t, then we're multiplying by t and t here, and here I'll multiply by 2t. You'll see that they will all add up to cancel off, and you still end up with V0. So the formula is the same. Similarly, in the same vein for here, because here will be t, here will be 2t, you still end up with V0 squared over 2. Hence, in conclusion, when you alter your frequency or the period of the AC wave, there's no change in terms of root mean square value of your voltage, your current, as well as the maximum or the average power.